Hello and welcome to this video tutorial, which is on AS Physics Paper 1 of the May-June session 2022. My name is Kagwe Munro and have been teaching physics at advanced level for the last 20 years. If this is your first time on my channel, please take a moment and subscribe to this channel and share the video. And without wasting time, let's go to the first question. In this first question, we are asked which term represents a physical quantity. A physical quantity. Meter is a unit. Percentage uncertainty is not a physical quantity. Flavor is not a physical quantity, but spring constant is a physical quantity. So let's look at more information about physical quantities. Supposing we are given a car like this. What is meant by a physical quantity? The term physical quantity is used to represent measurable features of an item. For example, this particular item, what kind of features can we measure? Right? A physical quantity is actually a number plus a unit. For example, we can say the mass of the car is 1,500 kilograms. Mass is that feature of this item which can be measured. Mass is a feature of the item which can be measured. So when we are looking at physical quantities, we've got to mention that feature of that particular item which can be measured. What else can we measure for this car? We can measure the weight of the car. Actually, this one can be measured directly, or it can be calculated or processed from the mass. We can also measure the height of this car from all the way from the ground to the hood or to the topmost part of this particular car. We can be able to measure that. We can measure the speed at which it is moving and say it is kilometers per hour. When you look at physical quantities, for us to completely describe a physical quantity, we have to state a number and a unit. 1,500 kilograms. In fact, this is the definition of a physical quantity. A physical quantity is defined by this equation, that it is equal to a number plus unit, or it is equals to the magnitude. That one is very important. We can also go ahead and measure the diameter of the car. We can see that we are giving the number and the unit. So in our previous question, meter was the unit. It's not a physical quantity. The physical quantity in this case is mass, weight, height, speed, diameter, and so forth. The item, you can see it is the car. A given item can have more than one measurable feature. It can have more than one physical quantity. Now, how about features which are not physical quantities? Features of an item which cannot be measured, such as the color of the item. For example, the color of this car, it's blue. We cannot take a measuring instrument and find its magnitude in the sense in which we determine the magnitude, in the sense in which we measure the physical quantity. The model of the car also cannot be measured. When it comes to taste, like for example, flavor of food, for example, cannot be measured. We cannot take a measuring instrument and measure taste or the flavor. They are not measured in the same way, the way we would measure physical quantity, and therefore they are not physical quantities. A physical quantity can either be measured directly using a measuring instrument, or it can be calculated or processed from other physical quantities. I've already mentioned this when I compare mass and the weight of the car. The mass of the car can be measured, and then the weight of this car on earth can be calculated. All right, that one's just an example. Other examples include length and area. This can be measured, but when it comes to area, we can calculate the area. I hope you do understand that. Let's look at other points about physical quantities. Some physical quantities do not have units. They are ratios of two physical quantities which have the same unit. What are some of the examples? Examples of physical quantities without units include strain. You remember strain when we deal with Hooke's law? Strain is the ratio of the extension to the original length. Relative permittivity of a given medium. It is equal to the permittivity of the medium over the permittivity of vacuum. Relative density of a substance. It is the density of the substance to the density of water. Refractive index of a given medium. The sine of the angle of incidence to the sine of the angle of reflection of the speed of the wave in that particular medium compared to the speed of the wave in vacuum or in air. Trigonometrical ratios such as the cosine of an angle, the ratio of the opposite side to the hypotenuse, efficiency of a machine, mechanical advantage velocity ratio. In other words, in physics, we do encounter some physical quantities which do not have units. That does not mean that the way they were derived, they didn't have units. They had units, but the way they have been defined, the way they have been derived is what makes them have no units. So I hope that particular discussion on that shed some light on physical quantities. Let's go to question number 2. In question number 2, we asked which two units are identical when expressed in terms of SI base units. Here we are using the concept referred to as homogeneity of physical equations. A physical equation or an expression is said to be homogeneous with respect to units if the units on one side is equal to the units on the other side. So we are going to compare joules per coulomb. For example, is it equal to kilograms meter squared per ampere per second squared? So what is it that we need to do in order to tackle this kind of question? For example, when we think about the joule, we realize that the joule is the SI unit of energy or work. We need to remember how work is defined. So that is the first thing that we need to do. We need to remember how that physical quantity is defined so that we can break it down until we express it in terms of the 7 basic physical quantities. There are 7 basic physical quantities. Force is not among them. Work is not. So we are going to say work is equals to force times distance. And then we break down force as mass times acceleration. This is how we define force. It is defined as the product of mass and the acceleration. In fact, force is defined as the rate of change of momentum, which is expressed as mass times acceleration. So at this point, we are able now to recall that the base unit of mass is kilogram. Acceleration is very easy to recall. This one is meters per second squared and distance is meters. So we can therefore express the joule in terms of base units, and it is kilogram is the SI base unit of mass. Meter per second squared is the SI base unit of acceleration, and of course meters is the SI base unit of length or distance. When you combine them, when you multiply this meter by this meter, that's how we get meters squared. So, but the joule is combined with the meter, it's combined with the second, it's combined with per coulomb, and so forth. So, when you look at joule seconds, for example, we are going to take the SI base unit of joule times the seconds, and that is where we get kilograms meter squared per second. However, this particular question requires you to test each one of them. So I will leave you to use this method that I've already shown you on how to go about arriving at or expressing named units like the Newton, for example, into a base unit. Otherwise, the answer for this particular question is supposed to be B, where joule seconds is same as kilograms meter squared per second. And I've shown you how it is arrived at. So go right ahead and test the others, and you'll find that joules per coulomb is not the same as kilograms meters squared per ampere per second squared. It is not. Similarly, C is not correct and D is not correct. Take your time, use the method that I've already shown you to show that the others are not correct. Let's go to question number 3. In question 3, we are given that a value for the acceleration of free fall on Earth is given as 10 plus or minus 2 meters per second squared. Which statement is correct? So here we have to test each one of these statements. This value is accurate but not precise. So we need to remember the definition of accuracy, or what is meant by accuracy. A value or a given value, whether it is a measured value or a calculated value, is said to be accurate. Is said to be accurate if it is close to the true value. Okay. Accuracy is how close a given value is to the true value. How about precision? Precision is simply the number of significant figures that are used. For example, in this particular question here, when we say 10 plus or minus 2, it means that the value could lie between 8 and 12. We know that the true value of the acceleration of free fall on Earth is 9.81. So you find that the value which is calculated and given this range is definitely going to be accurate. It is accurate because it is closer to the true value within this range which is given here. So that value will be accurate. But how about precision? 9.81 is 3 significant figures, and we can see the values we are getting here, they are 2 significant figures. So in terms of precision, this value will not be precise. It will not be precise. So here is the argument. The actual value of G is 9.81, 3 significant figures. G being equal to 10 plus or minus 2 meters per second squared means that it lies between 8 and 10. So it is accurate, but expressed to 2 significant figures and therefore not precise. And that is why our answer is A. This value is accurate but not precise. Let's go to question 4. In question 4, we are told that 2 cables are attached to a bracket and exert forces as shown. So there's a bracket and we've got these forces which are acting on that particular bracket. When you're given a question like this one, the first thing is to resolve the forces. But we must check what we have been asked to calculate. What are the magnitude of the horizontal and vertical components of the resultant of the 2 forces? Now, you will remember resultant force is the single force which represents all the forces which are acting on that object. For example, if I add 15 newtons and 6 newtons, I'm going to get one force which represents the 2 forces. That force is referred to as the resultant force. The resultant force can be resolved in 2 components. Or in the process of getting the resultant force, we ought to have resolved each one of these forces. So we have been asked the horizontal component of the resultant, which value is it? The vertical component of the resultant, again, which value is it? So in the steps which we follow to get the resultant force, the first thing is to resolve each one of these forces. For example, I get the 15 Newton force. I resolve it horizontally like that, and I'm going to get 15 cos 20, which is 14.1 newtons. I also resolve it again perpendicular to this other component, where I get 15 sine 20, which is 5.13 newtons. There are 2 things which stem from here. How do I know whether I'm using a cosine or a sine? That is one of the questions you should ask me. And the other question is, why should we resolve twice? To answer the first question, the cosine the component of a given vector in a given direction. For us to get the magnitude of the component of this vector in this direction, we find the angle that direction makes with the vector. That's why it's so important for you to be able to understand. The moment we get the angle that direction makes with that vector, then we immediately just use a cosine. And then we go ahead and find the second component of that force in a direction which is perpendicular to the first component. We make sure that the two components are perpendicular to each other so that we can treat them independently of each other. For example, now I can go and add this one and this one without bothering about this other one here. Yeah, the reason why we resolve in two directions which are perpendicular to each other is so that we can treat that particular component in that direction independently. We go ahead and resolve the 6 Newton force again twice, downwards and horizontally. Again, here we use the cosine because it is making an angle of 40 degrees, and here we use the sine. Now, after we resolve in two directions which are perpendicular to each other, like this one here, we can therefore add this force and this force the way we would add any numbers, so that we get one force which will be equal to 18 newtons, 14.1 newtons plus 3.9 newtons, we get 18 newtons. But when it comes to the vertical direction, since the two forces are acting in opposite direction, we are going to subtract the smaller one from the bigger one, and we are going to get 0.534. When we do 5.13 minus 4.6, we get 0.534. So the horizontal component of the resultant will be this one plus this one. We add all the horizontal components of the forces. Let us assume that there were more than two forces. We would resolve each force horizontally and vertically, and then we add all the horizontal components. The one force which represents all the horizontal components will be the horizontal component of the resultant force. Let me repeat that. It's very important. The sum of all the horizontal components of the forces, the sum of all the horizontal components of the forces represent the horizontal component of the resultant force, while the sum of all the vertical forces represent the vertical component of the resultant. And by that, we are going to see that our answer becomes this. The horizontal component will have a value of 18 newtons, while the vertical component will be 0.534 newtons vertically upwards. So let's go to question 5. In question 5, we are told that the curved line PQR is the velocity time graph for a car starting from rest. There are two things which we must know about a velocity time graph. The gradient of a velocity time graph represents acceleration, while the area under a velocity time graph represents displacement. Those are two things which you must remember about velocity time graphs. What is the question? What is the average acceleration of the car over the first 5 seconds? Remember, we have agreed that the gradient of a velocity time graph represents acceleration. But the question is asking us to calculate the average acceleration. The average acceleration is given by, we are going to get the velocity at this point minus the velocity at this point divided by the time the velocity took to change from this value, which is 0, to this value here. I repeat that one because it's very important. The average acceleration is given by final velocity minus the initial velocity divided by the time the velocity took to change from 0 to this value here. So, and when we do that, when we do this velocity minus this velocity divided by 5, it's like we are finding the gradient of the line PQ, the gradient of the line PQ. So, and that is why the gradient of the straight line PQ gives us the average acceleration, okay? The reason why the gradient of the tangent at point Q is not correct is because of the way the question has been framed. If the question had been framed to read like this, what is the acceleration at point Q? What is the acceleration at point Q? Acceleration at a point, we draw the a tangent at this point, and then we find the gradient of that particular tangent. That would be the answer if the question read, what is the acceleration at point Q? But this question is about what is the average acceleration of the car over the first 5 seconds. Let's go to question 6. In question 6, we are told that a ball is thrown horizontally with a speed of 10 meters per second above the horizontal ground. The ball hits the ground after a time of 3 seconds. Air resistance is negligible. What is the speed of the ball just before it hits the ground? So this is a ball which is traveling horizontally. We know that as soon as it is projected horizontally, it is going to curve downwards like that until it hits the ground, maybe at some point there. By the time it hits the ground, it's going to have 2 velocities. Just before it hits the ground, it will have a horizontal speed which is maintained at 10 meters per second, and there will be a vertical speed which it has gained over the time of 3 seconds. Very important. So this is what we have. By the time it hits the ground, it has this velocity here which is 10 meters per second, and it has this vertical velocity that it has gained for a time of 3 seconds. So in order to get this vertical velocity that it has just before it hits the ground, we use this equation, v is equals to u plus at. Okay? So when we have a situation like this, where air resistance is negligible, there is one point which you must remember, that the horizontal component of the velocity always remains constant. The horizontal component of the velocity always remains constant, and there is no acceleration horizontally because there is no force acting on the ball horizontally. That one is very important. The reason why the velocity remains constant is because horizontally there is no force acting on the ball. But vertically, there is a force acting on the ball which is equal to the weight of the ball. And that is why the ball is going to accelerate vertically. That's why when we say v is equals to u plus at vertically, we must say this, the final velocity vertically is equals to the initial velocity vertically plus at. Although the ball has an initial speed horizontally of 10 meters per second, vertically its speed is 0. Therefore, by that we get the vertical velocity is 29.43. However, it has a horizontal velocity. When you look at the question, we are asked what is the speed of the ball. The actual speed of the ball is the vector sum of the horizontal velocity and the vertical velocity. And when we look at it, this one is a hypotenuse. So in order to get the hypotenuse, we can use Pythagoras theorem. And that is how we get 31 meters per second. And that is why our answer is C. Let's go to question 7. An object is moving along the ground in a straight line at a constant speed. An object is moving along the ground in a straight line at a constant speed. That means that the velocity is constant, and therefore the acceleration should be 0. Which statement about the resultant force acting on the object is correct? You see, when the object is moving in a straight line and its speed is constant, it means that its velocity is constant. Its velocity is uniform. That means that the acceleration is zero. If the acceleration is zero, from Newton's second law of motion, F is equals to ma, we will see that the resultant force on the object is zero. So this is the argument. Since velocity is uniform, the acceleration is equal to zero. Hence, from F is equal to ma, the resultant force is equal to zero. And that is where the correct answer is D. The resultant force acting on the object is equal to zero. Let's go to question 8. Water flows out of a pipe and hits the wall, as shown. When the jet of water hits the wall, it has a horizontal velocity v and cross-section area A. The density of the water is rho. The water does not rebound from the wall. What is the force exerted on the wall by the water? When you look at this question, you might argue out that you've never seen this kind of equation and that it is out of your syllabus. It's not out of the syllabus that we are studying at AS, because we have defined the term force as a rate of change of momentum, and that is where we are going to begin from when we want to derive that equation. So let me take you to the next slide, where I've written down the points that we need to consider when we are deriving this equation. So the equation that we are to derive here is derived like this. Force on the water is equals to rate of change of momentum of the water. In 1 second, the distance moved by this water is equals to the speed times time, which is equals to v times 1, which is just equal to v. Anything multiplied by 1 is just v. So this is from basic general physics or kinematics. The volume of water, this is the volume of a cylinder because the shape of the water is in the shape of a cylinder. So we are going to get the cross-section area times the length of the cylinder, which happens to be equal to the distance that is covered by that water in 1 second, which is A times D. And our distance is V. Since our distance is V, the volume is going to be AV. Mass is density times volume. We have just derived this, that the volume is AV. So you just need to add a rho AV. Force on the water is equals to rate of change of momentum. So we are going to divide the change in momentum by 1. Change in momentum is mv minus mu divided by 1. M into v minus u, because when you divide anything by 1, it's just that number. So, but the mass is rho AV. We have just seen that. That is the mass. And when we substitute, we are going to get 0 as the final velocity. The initial velocity is minus v. And that is where we get minus rho AV squared. So where does the minus sign comes from? It comes from the way we have defined our problem. Force on the water. But the question is asking us to calculate the force exerted on the wall by the water. So by using Newton's third law of motion, we just ignore the negative sign, and that is how the answer turns out to be D. Okay, let's quickly go to question number 9. Question number 9 is on projectile motion. What do we have? A projectile is launched at an angle above the horizontal ground and travels through the air. This is just like the question we have done in horizontal projection. At any one point, we are supposed to resolve that velocity. At the beginning, we resolve the velocity horizontally so that we get the horizontal component of that velocity. And that horizontal component will remain constant throughout. So at the highest point, this projectile has got a horizontal component that way, but vertically, its velocity is momentarily 0 at the highest point, because it is at the point of now starting to move downwards. So all the way from this point to this point, it's moving up, it's moving up, moving up, moving up, but that velocity is reducing until it is just equal to 0 at the highest point. That is the vertical velocity. At the highest point is 0, but horizontally it is moving. What is the question? The projectile reaches its maximum height at position X. Assuming that no upthrust acts on the projectile, which diagram shows the directions of the force or forces acting on the projectile at position X? When we read the question carefully, is that this projectile is moving through the air, is launched at an angle theta and travels through the air. You see, it travels through the air, so there is air resistance. Since it is at this point, it has got a horizontal speed that way, air resistance must be acting on it in that direction. The other force that is acting on it is its own weight, vertically downwards, and that is why the answer is B. So over here, I've shown you how the answer is arrived at. At this particular point, there is air resistance on the projectile because the object is traveling through air. Unlike the other question where we were asked to ignore air resistance, there is also the weight of the projectile. That's why the answer is B. Let's look at question number 10. What is a statement of the principle of conservation of momentum? Again, this is one of those questions where we are asked to pass some judgment on statements which are given. So it's important to read the question carefully. A principle of conservation of momentum. A force is equal to the rate of change of momentum of the object upon which it acts. Although this statement is true, it is a statement which is used to define force. It is a true definition of force. However, that is not what we've been asked to determine. So this question, the reason why the examiner sets this question is just to test. There are some students out there who go, cramming certain definitions, certain concepts, hoping that one will help you in the exam. You should know the definition of these physical quantities properly, and not just a cram in the hope that one of them comes, and you cannot just get that kind of question being that simple. B. In a perfectly elastic collision, the relative momentum of an object before impact is equal to the relative momentum after impact. Although the statement is true, again, it has nothing to do with the conservation of momentum. C. The momentum of the object is the product of the mass of the object and its velocity. Again, this statement is used to define momentum. It is not stating the principle of conservation of momentum. And D is the correct one. The total momentum of a system of interacting objects remains constant, providing no external forces act on the system. So D is the correct choice. We're going to stop at that point. In the next video, we'll continue with the rest of the 30 question. Again, if this is your first time on my channel, please take a moment and subscribe to the channel and share this video, because this will help me to continue developing content like this. See you in the next video.